Hi, my name is Nolan Majeski. For my project, I'm going to be using a life-size slingshot with this resistance band and these T-posts. This slingshot will simulate a spring and the force in a spring equation, which is negative kx, where k is the stiffness in a spring or the resistance in our band, and x is the distance that I'm going to pull it back. Once the band or spring is stretched back, it's going to hold potential energy, where the potential energy equation of a spring is 1/2 kx squared, k again being the resistance in the band and x being the distance is stretched back. When I release the band, it's going to launch the objects and give the objects kinetic energy, who will have an equation of 1/2 mv squared, where m is the mass of the object and v is the velocity that when it releases from the spring. The first object I'm going to launch is the basketball, and then I'll do a football. And then it's the softball, the baseball, and the golf ball. Each object that I launch is going to be lighter than the object before it. So the objects should launch further and further as we get into the project. Using the energy balance equations, the potential energy stored in the spring when it is stretched should equal the kinetic energy of the object as it releases from the band. If we know the resistance in the band, k, the distance that it's stretched back, x, and the mass of the object, all we can do is solve for v and for kinetic energy. Once I launch the objects and they have kinetic energy, it will be nothing but a projectile motion scenario. The first object is the basketball. The second object is the football. Object is the softball. The fourth object is the baseball. The last object is the golf ball. As seen in the previous clips, our assumptions about the distance of each object being launched were correct. Notice how the basketball traveled the least amount of distance, while the golf ball traveled the furthest. This happened because a basketball weighs a whole lot more than a golf ball, and the slingshot was able to launch it a whole lot further. In this project, we ignored all factors of friction in the resistance band and air resistance. If we were to consider these factors, we would have to take into account things like wind and the shape of the object and whether it was aerodynamic or not. We talked about how we can set the potential energy of the spring equal to the kinetic energy of the object and solve for our unknowns. So, if we know the resistance in the band k, the distance that it was stretched back by me, x, and we weigh the object and find a mass, we can solve for the velocity as it comes off the band. Using all the equations, now let's solve for the velocity of the basketball. So if we have the given information, the mass of the basketball being 0.625 kilograms, the K of the resistance band being 500 Newton per meter, and the distance that I stretched it back, x, to be 1 meter, we would set the potential energy and the kinetic energy equation equal to each other, Notice how our only unknown is the V. Solving for V, we found that the velocity leaving the resistance band was 28.3 meters per second. Now we're going to compare it with the golf ball and see the difference. Now, when we consider the golf ball, the only difference here is going to be the mass. It's the same situation. We use the same K in our resistance band and the same distance stretched back. The mass of the golf ball is now 0.04593 kilograms. Again, V is our only unknown, so solving for V, we found that it was 104.3 meters per second, which is almost 4 times as much as the basketball's velocity, which explains why it traveled so much further. Similarly, you can do this with all of the objects, replacing the mass, solving for the velocity, but I think you get the idea. As the mass increased, as the mass decreased, the object went further. Just like we manipulated the mass in our equations, we could have also manipulated the spring constant K, or the resistance in our band. Well, I used this resistance band, which had a decent size K. This resistance band was a whole lot stiffer, so that 500 could have been increased to a much larger number. Doing that, you'd see it would add a whole different twist on the equations. Alright, thank you guys. This was my dynamics project. I hope y'all were able to learn something and be able to see the correlation between the different variables you can manipulate in our energy balance equations. Had fun with it. Thank y'all.